chapter on Laplace transform. That's a technique to convert a differential equation, say first order or second order, with some initial conditions to an algebraic equation. And we try to solve the algebraic equation using simple algebra. Usually it should be okay and it should be manageable, and we get some answer for the algebraic equation, and then we do an inverse Laplace transform back to so-called the analysis case, analysis equation, where there's a function and its derivative involved. Right, so the last bit of the lecture on Monday was this formula here for the Laplace transform of a derivative. So we want to convert ordinary differential equations to algebraic equation. We should be able to take the Laplace transform of a derivative, right? So if we can't, then how to convert from an ODE to an algebraic equation. Okay, so here's the key formula. The Laplace transform of the derivative of a function f is equals to, or the Laplace transform of the function itself multiplied by the variable s. Remember, the Laplace transform of a function of t, say, is another function, and this second function has input variable s, not t. So as I said last lecture, there are actually four things in play. The function f with input variable t, and then the Laplace transform function with input variable s. So four things. And so it's the s times Laplace transform of f minus, okay, f at 0, this is a number. Right? So you see on the right, on the left hand side we have a derivative, and then you have the Laplace transform. On the right hand side we have the Laplace transform, which is just a function. There's no derivative on the right hand side. So you have an expression, it's actually an algebraic expression in s. Right, so I show you why we have such a formula. Today we move on to generalize this. Say if I look at the second derivative, well, the second derivative is just the derivative of the first derivative. So Laplace transform of the second derivative is going to be s times the Laplace transform of the first derivative, right? Minus the first derivative at 0, t equals to 0. Then what we do is play this game again, where we have the formula in the red box put here, and Laplace transform of f prime. So now we don't have any more derivatives on the right side. So it's just s squared Laplace transform f minus s times, and we open up the s will just multiply in, s times f0 minus f prime of 0. As I stress, f at 0 and f prime at 0, they are numbers. So this part is just going to be a number, a constant, and then there's a constant here multiplied with s. So it's a linear expression here, and this quadratic. But quadratic, there will be some function of s here for Laplace transform of f. So this part may, most likely will not just be quadratic s squared times constant. So this is the second formula, and certainly we can go on Laplace transform with third derivative. There is a pattern to the numbers that come out. I think it's not too difficult to see the pattern, and it's over here. The Laplace transform of this f bracket n is the nth order derivative of f. Yeah? And on the right hand side is just a s power n times the Laplace transform f minus s power n minus 1, f value is 0, and so on. So I don't think you need to memorize this. To start off, it would be good to remember the first formula, and you can see, you can get the second formula from the first easily. Right? So after a while, after you work a few of these examples, then you find that this one is very familiar, then the second one is also quite familiar. So you may not count it as memorizing anymore. All right, let's look at an example. Let's say Laplace transform of sine squared t. Now there could be many ways of finding the Laplace transform. One way is the direct integration by definition. Here we're going to illustrate the formula, Laplace transform for the derivative. And there are other ways, because there are many properties, many equations, identities involving trigonometric functions. So you can play around with those, rewrite sine squared in terms of other trivial functions, and apply the Laplace transform through linearity. Okay, so for this example, I want to use the Laplace transform of derivative just to illustrate the formula, right? This formula here. Right, so you look at the right side, you need to evaluate the function at 0 at some point. And so here, if I set my ft to be sine squared t, then at 0, sine squared t is 0. Then what about the Laplace transform of sine squared t? Yeah. The Laplace transform of the derivative here, yeah, is that, well, we can differentiate sine squared t with power rule and chain rule, right? 2 sine t cosine t. Then, see, we don't have a Laplace transform of sine t times cosine t at once, right? So, but we have a formula for Laplace transform of sine wt. Right? So that's why we convert this 2 sine t cosine t to sine 2t. So that we are looking at w divided by sine squared, w divided by s squared plus w squared. Right, so here w is 2, so we have 2 over 2s squared plus 4. Right, so we've got this part here. F at 0 is always 0, so we essentially just create 2 over s squared plus 4 to s times the Laplace transform f, which is what we want, right? So to finish up, we just divide by s throughout, and move the s over. So Laplace transform of sine squared t is just this Laplace transform of f prime divided by s, right? Move the s down. So it's just 2 over s times s squared plus 4. So that's the answer. So this one way of calculating the Laplace transform of sine squared t through this formula. You can, let's play around, say, write the sine squared as what? In terms of cosine 2t, right? You can do that, right? Okay, this example, I find the Laplace of t times sine alpha t is a bit involved, right? Again, I want to illustrate this formula, so let's set up notation. Ft is t times sine alpha t. Then the formula involves the derivative, right? So if you differentiate differentiate t times sine alpha t, you need the product rule of differentiation. And so you differentiate t, you get 1, then write sine alpha t, then plus t times derivative of sine alpha t, then you do cosine alpha t, the chain rule comes to differentiate alpha t, you get alpha. Right? So there's alpha times t times cosine alpha t. This example, I want to illustrate the second formula involving the second derivative. So when you differentiate this derivative here, right, the first one is just straight derivative of trivial function. So you get cosine alpha t times alpha, right, the derivative of alpha t. How come there's a 2 here? Because there's a second term here, and when you differentiate the product here, right, t times alpha, t times cosine alpha t, when you use the product rule, the first term will give you a times cosine alpha t. Right? So that's why there's another 1 and 2, right? Then the second term here, you differentiate the cosine alpha t. Right? So they'll give you minus sine alpha t. And chain rule comes to differentiate the alpha t, you get alpha. Right? So that's why it's an alpha squared. Minus alpha squared t sine alpha t. All right, so this example, we exploit the property that when you do a second derivative of sine, you essentially come back to sine. You differentiate sine with cosine, then you differentiate cosine, come back to sine, or there's some sign change, right? The minus sign there, but you do get the sine function back, the second derivative. So even if you put a t there, well, the sine alpha t will also come back. And this time it actually counts as minus alpha squared t times sine alpha t. So we want to play around with this. And so this is just going to be 2 alpha cosine alpha t minus alpha squared ft. Right, so this allows me to apply linearity when I take the Laplace transform of the left hand side is just going to be Laplace transform of the second derivative. On the right hand side, we have a difference of two functions of t, right? One function of t minus another function of t. Then, okay, this function is cosine alpha t, then there's a coefficient 2 alpha. Coefficients are just real numbers. The other function, ft, has a coefficient minus alpha t, minus alpha squared. So this is just a difference of two functions. So when you apply Laplace, you can apply Laplace transform individually on the function cosine alpha t and ft. So by linearity, you get this. You can pull out the 2 alpha from Laplace transform alpha, 2 alpha cosine alpha t. Similarly, with Laplace transform here, you can pull out the minus alpha squared like this. Okay, this Laplace transform as the second derivative, we have a formula. So we equate this expression to what's on the right-hand side. S squared Laplace transform f minus s times f at 0 minus f prime at 0. So it's at this stage that I realize, oh yes, I need to calculate f at 0 and f prime at 0. So f at 0, I need to go back up here and plug in 0 for t. I mean, if you look at the note, we write down the function ft equals to t sine alpha, then immediately evaluate at 0. Some people ask, why must you do that? Must you always do that? Well, not necessarily. You do it only when it is necessary. And in this case, when we use the formula, we need to calculate f at 0. Right, so this part goes to 0. What about f prime at 0? So we look at this second function here. F prime is sine alpha t plus alpha t times cosine alpha t. Right, so you plug in 0 for t, sine 0 is 0, and there's a t here, so second term is also 0. So this also goes to 0. Right? So now we are looking at equation. Okay, Laplace transform of f is what we want, right? Then Laplace transform cosine alpha t, need to call that out. So over here, let's see. Okay, there are two of them, Laplace transform f and Laplace transform f here. Then there's the minus alpha squared and s squared. So you combine these two. Then you need to calculate the Laplace transform cosine alpha t. So that's the formula we have. The cosine alpha t has a Laplace transform with the s in the numerator. Let's put that in, and we are almost done, right? This is just a fraction, a rational function, a polynomial function of s divided by a polynomial function of s. So a rational function of s, algebraic. There's no derivative involved. Right? The left-hand side similarly, it's just Laplace transform f, and then s squared plus alpha squared. So if you want Laplace transform f, you just divide throughout by s squared plus alpha squared. So here the exponent goes up to 2. And so we have Laplace of t times sine alpha t is just 2 times alpha s divided by the square of s squared plus alpha squared. Right, so that's the answer. Right, so this is an example illustrating how to work with the formula for the Laplace transform of derivative, Laplace transform of second, or the two derivatives. So now we move on to this initial value problem. Initial value problem is a differential equation together with some initial conditions on the function. Okay? Let's set up. We have, say, a second order differential equation, linear, A and B are constant, and the R on the right side is a function of t. So it's a linear, second order linear function, second order linear differential equation. Y double prime plus AY prime plus BY equals to RT. So Y here is a function of t. At 0, the t equals to 0, y is the function is value k sub 0, and the derivative has value k sub 1. Right? Let's say the Laplace transform of this RT on the right side is capital RS. As I said last lecture, we reserve certain letters, alphabetic letters. If we use small letters for the original function and capital letters, the corresponding capital letters for the Laplace transform, because we need to keep track of all the functions and transforms that come out. Right? That's the first step. We take the Laplace transform of both sides of the differential equation. Right? The left-hand side is the sum of three terms, sum of three functions, and some of the functions that are derivative. So we use the linearity property, that is apply Laplace transform on each term, and then add up the Laplace transform. Right? So we take the Laplace transform. I'll be taking the Laplace on the second derivative y double prime. So I'll need this formula here. Okay, I just pull out the formula and put it here. Of course, we're going to set f here to be y, right? And y here, and then y and y prime. So that will take care of the first term. That means these three terms over here come from the Laplace transform of y double prime. Okay, so move on. A Laplace transform f prime, this is a formula, so we are setting f to be y, so we have Laplace transform y prime, giving these two terms. The a there belongs to the Laplace transform of y prime, so it belongs to these two terms. And with the last bit here, nothing much to do. You just apply Laplace transform onto y, and you get L of y. Okay, if we use this notation, reserve notation, capital letter for the Laplace transform of function written in small letter case, then this equation can be written in more simply. This you can write a capital Y here. Right, and then this is a little y is 0, little y prime is 0, and so on. This you can write a capital Y and a capital Y here. Then on the right side, it will be a capital R. I didn't highlight this part. It's just that, nothing much. But my point that the equation then looks more algebraic. We don't have this function notation that you can use a capital Y for the Laplace transform of little y. Okay, you put in the initial condition. Alright, so y at 0 is k sub 0, so you put a k sub 0 here and a k sub 0 there. And y prime at 0 is k sub 1, so you put a k sub 1 there. So my point is, we have these capital Y or L, capital L of Y. Then the other terms that don't have this capital L, they are going to be polynomials in S. Polynomial in S. Polynomial can do have constant terms sometimes, right? So we have constants along the way too. Okay, so after step 1, we will end up with, or we have intermediary equation like this, algebraic equation from here. Right, then solve for the Laplace transform of y. That means make Laplace transform of y the subject of the equation. All the others you just push to the right side, algebraically. Yeah, so you'll be moving terms over and dividing it. So you end up with some expression like this. You don't need to memorize this expression. When you have an algebraic equation in front of you, like capital Y squared plus 2 times capital Y plus 3 equals to 5, how you can solve for capital Y algebraically. So that's what we're trying to say here. You don't need to memorize this, you're just going to solve for Laplace transform of Y. See? Then we want Y, so the last step would be to apply inverse Laplace transform. Then there will be some function of S here, usually rational function. Then you apply inverse Laplace transform. You may need to look at a table of values now, Laplace transform. So before you apply inverse Laplace transform, you may need to do some algebraic manipulation so that you get your expression in the form of values in the Laplace transform table. Okay, so then you can read off the values from the table and write down the answer. Okay, so the solution y as a function of t is obtained after applying inverse Laplace transform. Okay, remember this diagram at the beginning of this chapter. If you have it, then you can look at it, and then I can tell you the 4 steps that we've just discussed can be written in. So the first step was what? We applied Laplace transform to the differential equation, right? So that's step 1, is you go from ODE to an algebraic equation. Then step 2, you have algebraic equation in front of you, simplify. Sometimes you need to combine some constant terms, sometimes you need to combine some linear terms in S and so on. Right? So this manipulation of the algebraic equation. And when you manipulate algebra, what are you looking for? You are looking for Laplace transform of y. Just now, make that as a subject of the equation. So that's this part here, solved by simple algebra for Laplace transform of y. Now, all the other terms beside Laplace transform of y we push to the right side. So that's this part here, solved by simple algebra. Then you get to step 3, the so-called solution of the algebraic equation. Laplace transform of y is equal to some rational function in S on the right side. Okay? So that's step 3 here. Right? Then the last step would be go back, apply inverse Laplace transform. You get back a function y of t, and that's the solution of the ODE. Okay, so you have some idea what's going on and why you apply Laplace transform. The move terms around algebraic and apply inverse Laplace transform is to go from ODE to the solution of the ODE indirectly. All right, let's look at an example. Let's say y double prime plus y equals to e to the 2t. Solve this differential equation with initial conditions here. Y is 0 at t equals to 0 and y prime is 0. Y prime is 1 when t is 0. So take Laplace transform both sides and use the initial condition. So the left side, Laplace transform of y double prime plus y, you use linearity, right? So the first term here, Laplace transform of y double prime, using this formula here, put the terms in. Right, then Laplace transform of y is written down here. The right side, e to the 2t, I'll need this formula. Laplace transform e to the at. That's 1 over s minus a. So put that in. Right? A here is obviously 2, so 1 over s minus 2. Right, so now we have an algebraic equation in front of me. I need to put in the initial condition, right, to simplify this part. So put that in. Y is 0 at t equals to 0, this part is 0, then y prime is 1 when t is 1. So when t is 0. Right? So now solve for Laplace transform of y. Make it the subject of the equation. All the others you just push to the right side. So let's see. Laplace transform of y, Laplace transform of y. So you factor s squared, factor Laplace transform of y out. Then you'll be left s squared plus 1. Okay? Then that's 0, can forget it. Minus 1 you push to the right side. So that's why there's 1 plus this 1 over s minus 2. Then the factor of Laplace transform of y found just now was s squared plus 1, right? So push it to the right side. It's 1 over s squared plus 1. Okay, simplify, in a way simplify first, that combine as single fraction of common denominator, s squared plus 1 times s minus 2. So I think this part I can leave to you. It's just simple algebra. Then now the problem is, to finish off, you just need to take inverse Laplace transform, right? And you get y on the left side and then an answer on the right side. But the right side, you need to take Laplace transform of this. Normally, the list of formulas would not include something like this. It's quite complicated, right? So you would need to simplify this or rewrite this in the form that you can use formulas in the table. So this usually involves partial fraction. Because if you look at the Laplace transform we have so far, they are rational functions of s. Rational functions mean polynomial. And the polynomials are simple polynomials like s minus 2, s squared plus 1, s squared plus w squared. So here I want to split this into smaller fractions called partial fractions, like this. Something over s minus 2 plus something over s squared plus 1. Right? So looking at the numerator, the degree of this polynomial is 1. The degree of the polynomial in the denominator is 3. So I don't need to do any long division. If you have something like a degree 4 polynomial in the numerator and a degree 3 polynomial in the denominator, you start off by long division, by using long division to divide out, get a quotient which should be a polynomial in S, plus a remainder which you write in the numerator, and well, this term here, now this is called the divisor. So you need to, if necessary, perform long division to reduce your your rational function to the form where the degree of the numerator is less than the degree of the denominator. Okay, so once we are there, then we start writing in partial fraction form. Then you wonder, if you have a polynomial in the denominator, can you always factor and then write it this way? And the answer is yes, by something called Gauss's theorem. Right, so we are always able to split complicated rational function into partial fraction. Okay, so how to get these numbers? Right, the same principle applies. This is a degree 1 polynomial. What you write up here will be the polynomial degree lower than degree 1, that is constant. And this one, s squared plus 1, the degree is 2. So you look at polynomials with degree less than degree 2, it will be linear. Right, so if it turns out that b is 0, then you just have a c, maybe c could be 1. Then you have a degree 0 polynomial in the numerator. But you don't know, right? At the beginning, you don't know what the polynomial is in the numerator. So you just allow for a degree 1 polynomial there. Yeah, even though maybe after solving for b and c, you find that b is 0 and c is some non-zero number. Alright, so how to get a, b, and c? Normally we will just combine the right hand side into one big fraction. Then the numerator will be a polynomial in S involving A, B, and C, the coefficient. Then we will equate coefficient. So multiply both sides of this equation by the denominator S minus 2 times S squared plus 1 and equate the numerator. So this is what I'm doing here. So A times this plus BS plus C times S minus 2. Right, so we are going to compare coefficient. Left hand side is a polynomial, it's actually a linear polynomial. Right hand side is, well, it starts off because there's S squared is a quadratic polynomial. So we open up, you get this. Then collect the terms to the same degree. Yeah, so A plus B is a coefficient S squared. Minus 2b and c, the coefficient s, and the other terms a and minus 2c, no s there, that's the constant term. Right, so from here we start by comparing coefficient. Do it systematically, yeah? So degree 2, the s squared. No s squared term on the left side means the coefficient of s squared, you write it, is 0. So a plus b has to be 0. We'll go down, say s. Well, there's an s there, the coefficient 1. This coefficient of s is minus 2b plus c, so minus 2b plus c has to be 1. And lastly, the constant term is minus 1, and this is over here the constant of a minus 2c. Right? So a minus 2c is minus 1. Okay, so we usually keep our fingers crossed that we're able to solve for the unknowns, A, B, and C. So let's see how this goes. Looking at second equation, it's a minus 2b plus c, so I'll double the first equation and then combine and add up. So we add up the 2b's cancel, 2a plus c, 0 plus 1 is 1. Right, this one, I'm going to use a third equation. I see a minus 2c, so I'll double this equation. Yeah, and 4a plus 2c equals to 2 and add up. Alright, so you add up these two. Oh, sorry, you get this, and then now this we, let's see, a is, oh, I see. Now we combine or compare these two equations. You add them up, you get 5a equals to 1. So a is 1/5. And this equation here will give you b. B will be minus 1/5. And this equation will give you c. 3/5. Right, so in the notes, the answers are just given. So if you're curious how you get that, never done this before, and these are the details. And after looking at it, you find the key points are what? You have a fraction, yeah, or two fractions, you combine the two fractions, and then compare the numerators. Right, so now our rational function, s minus 1 times, divided by s minus 2 times s squared plus 1, used to be this. Now we know the values of a, b, and c, put them in. Okay, so the first one is okay in that I have a formula for the inverse Laplace of 1 over s minus 2. The second rational function here, I recognize the denominator s squared plus w squared. Alright, so w will be 1, so s squared plus 1 squared. Okay? Then the numerator, and this will be the form, the Laplace transform, the going cosine wt and sine wt, right? So I'll split this to s over s squared plus 1 and 3 over s squared plus 1. And you take the inverse Laplace transform and you get answer. Okay, now with the answer in front of us is the solution of the first equation. You'll be tempted to compare. If you use the techniques in chapter 1 to solve this, how will you do it? How will you do it? You first find the homogeneous solution, right? To y double prime plus y equals to 0. So you get a homogeneous solution. After that, you need to find a particular solution, right? e to the 2t then for this. And then you get a solution to the differential equation as homogeneous part plus particular solution. The solution will involve two unknowns, say C1 and C2. To find C1 and C2, you need the two initial conditions. Then you sub in these numbers, and then you solve for C1 and C2 to get this solution here. Right? So for this example, the old way of doing it is not that much longer. Not that much longer. So this presents an algebraic way of solving the differential equation. The other thing is, if I don't have the initial condition, am I able to use the Laplace transform? No, right? So if you don't have the initial conditions, no chance to use the Laplace transform. You will have to use the techniques in chapter 1. Okay, let's say I want to find the Laplace transform, find ft of Laplace transform of ft given as 1 over s squared times s squared plus w squared. Okay. This is the form. Oh, I see. I may have omitted a slide. Now it's 12:44. Let's take a short break while I can rearrange the slide around it. This example is to calculate or involves the Laplace transform of an integral. Right, so let me see. I'm going to put the slide after this one. So let's take a short break. 12:44. 10 minutes. Let's use the 12:54.